Good evening, students. In the last lecture, we have started our discussion on thermodynamic relations, and we have seen the Maxwell relations and TDS equations. Now we will see the remaining part. First, we will see the Joule-Thomson coefficient, and then we will see the Clapeyron equation in this lecture. So, let us start our discussion with the Joule-Thomson effect. Although Joule-Thomson coefficient is given in the syllabus, we should first understand what is the Joule-Thomson effect first. Without understanding this Joule-Thomson effect, we will not understand what is Joule-Thomson coefficient. So first let us understand what is Joule-Thomson effect. This Joule-Thomson effect is also known as Joule-Kelvin effect. It is also called as Joule-Kelvin effect, or it is also called as Kelvin Joule effect. Kelvin Joule effect. So simple terms, if you say, it is called as same enthalpy effect. So these are various names of the same thing: Joule Kelvin, Kelvin Joule, same enthalpy. So what happens basically in this one? Okay, so in order to understand this, let's say there is a tube here. For this tube, you have introduced a valve in between. This is a throttle valve that you have inserted in that particular tube, and consider this side to be a section 1 and the other side to be section 2. So this is the throttle valve that you are having across a pipe, and if you have this kind of setup, you will obviously have certain pressure here, certain pressure here, P1 and P2. You will have volume 1, you have volume 2, you have temperature 1 this side, you have temperature 2 this side, you have U1 this side, you have U2 this side, so on like that. You will having so many properties here. So if you have these many properties keep changing across this valve, and you will have this enthalpy to be equal on both sides. This is the concept of your Joule-Thomson effect. So what happens here means, in spite of change in various properties across the throttling valve, the enthalpy will be maintained same. So this maintaining of the same enthalpy is nothing but the effect which we are speaking about here. This effect is called as Joule-Thomson effect. Okay, this will happen if you do the throttling in a slow manner. So that's what you will get here. So based on this concept, we will have a concept of Joule-Thomson coefficient also. Joule-Thomson coefficient. So what is this concept of Joule-Thomson coefficient? For understanding this, we will have to take the T So this is my temperature versus P plot here. So in this plot, if I have a certain point here representing my temperature and pressure initially at point 1, that one I have shown here, right? So towards my left I have shown 1 now, that one I am showing here. If this process 1 has so and so pressure and temperature, and you will have points 2, let me call this as 2a. There may be a situation where it will go to the other temperature and pressure, that will be 2b. There will be situation where it will go to the other pressure and temperature, it will be 2c. It will be 2d, other pressure and temperature, 2e, and so on. So if you observe carefully, all these lines, all these points will lie on a single curve. This single curve is nothing but a constant enthalpy curve. So this is nothing but your constant enthalpy process. Based on this curve, you will get a coefficient here. That is a relationship between your pressure and temperature. Since temperature is on your y-axis here, you will take it as dt by dp here, and that too at a constant enthalpy, and you will name this slope with mu j here. This mu j is nothing but your Joule-Thomson coefficient. So the Joule-Thomson coefficient is represented with mu, j being Joule. Joule-Thomson coefficient represented with mu here. So that's how you will define the Joule-Thomson coefficient. So it is defined basically on a TP diagram for an isenthalp. What is isenthalp? Isenthalp is nothing but a constant enthalpy curve or line. So it's a constant enthalpy curve or line. So based on that constant enthalpy curve or line, you define your Joule-Thomson coefficient. So in order to further understand this Joule-Thomson coefficient, we should understand the concept of inversion curve. What is the inversion curve basically? It is a curve that is passing through the maxima of constant enthalpy curves. These constant enthalpy curves are also called as isenthalps. Just now we have seen they are called as isenthalps. So the curve passing through the maxima of constant enthalpy curves is called as inversion curve. In other words, if I have to express the same in very simple form, simply inversion curve is nothing but mu is equal to 0 curve. Okay, mu means mu j, or the slope, or the Joule-Thomson coefficient. If the Joule-Thomson coefficient is equal to 0, that curve will give you an inversion curve. How an inversion curve will get, we will see here. For this, let me take this xy axis here. So on this my xy axis, I will have temperature and pressure here. Temperature and pressure. If I draw an isenthalp on this, it is going to look like this. So this is for H1 is equal to constant, and this is for H2 is equal to constant. Likewise, I can have so many isenthalps here. All these isenthalps, if you look at carefully here, they are having certain maxima here. So if I keep joining all the points of this maxima, I'll get a curve like this, and this red color curve is nothing but my inversion curve, which is also called as mu is equal to 0 curve. So basically this inversion curve will pass through the maximas of your isenthalps, maxima of your constant enthalpy lines. Okay, so this is what you will get here. So based on this, towards your left, if you observe, your pressure and temperature are increasing positively. That is, the relationship between the pressure and temperature is a direct relationship on the left of the inversion curve. On the right of the inversion curve, it is the inverse relationship. So here you will have plus value for your mu j, that is Joule-Thomson coefficient. On this side you have minus value for your mu j, and this side you will produce cooling, this side you will produce heating. So this is a cooling region and this is a heating region. So that's how your inversion curve will look like on a TP diagram. Similar thing you can have it on a TS diagram as well. If I show it on a TS diagram, this is how it is going to look like. Let us have a look at that as well. I don't think it is required. Some wrong option is chosen here. Yeah. So let us now look at how my TS diagram looks like for my mu is equal to 0 curve. For this, let me take one isenthalp here, H1 is equal to constant, and one more isenthalp here, H2 is equal to constant. Basically it's a curves. So this is how it is going to look like. And then if I keep joining these maximas, okay, so I'll get a curve here. This red color curve is nothing but mu is equal to 0 curve, or simply inversion curve you can call it. So that's how inversion curve will be like. And towards my left of the inversion curve, I'll get cooling effect. To the right of it, I'll get the heating effect. And this side you have positive relation, and this side you have inverse relation, that is minus you will get here. So that's the use of your Joule-Thomson coefficient. Based on the Joule-Thomson coefficient, you can tell whether the process is going to be a positive process or a negative process, or a heating process or a cooling process. What is the relationship between pressure and temperature? You can easily tell based on the Joule-Thomson coefficient. Okay, so that's the story of your Joule-Thomson coefficient and Joule-Thomson effect. Now we will move to the next concept, that's the Clausius-Clapeyron equation. Generally this is also called as, also known as, Clapeyron equation, because you have Clausius inequality that you will use here. That's why people call it as Clausius-Clapeyron equation. Without that also you can simply call it as Clapeyron equation. But before we go into this equation, we should understand certain basics of phase transformation process. If I have to represent the phase transformation in three forms on a single PT diagram, pressure versus temperature diagram, then this is going to be like this. Maybe that should be better line. Yeah, so this is how it will be like, and this point you generally call it as a triple point. This point is a triple point, and this side you call it as a solid state, this side you call it as liquid state, this side you say it as a vapor state, liquid state, and this side you have solid state. Okay, and in this thing we should also understand solid to liquid and liquid to vapor transformation you will have. If it is a solid to liquid transformation, between solid to liquid, then you should call it as a fusion. Generally it is called as fusion. And if it is between liquid state and vapor state, it is called as vaporization. And if it directly going from solid to vapor or vapor to solid, then you call it as sublimation process. So in each case you will have the latent heat of fusion, latent heat of vaporization, latent heat of sublimation, and so on. So that's what you will have here. So in this process I would like to take any two points here to get the derivation for my Clapeyron equation. For that purpose, what I am doing is I am choosing a point P here, and I will take a line here. This is my point P, and correspondingly I will have one more point here on my x-axis, which is T. Also, for a differential change here, I am considering one more point here, that is P plus dP. I'm considering for I'm considering only infinitesimally small change here. Although I'm considering infinitesimally small change, I'm showing you it in a zoomed form here for the sake of clarity. So here it meets this line, and then I will put it down towards my x-axis, and this will be my t plus dt point. So from P to dP and T to dt, it is moving. So there is a differential change here. I would like to account for this differential change here. So this being my initial state and this being my final state, initial and final. I represents initial, F represents final states. So from my initial to final, the process is happening here. I'm taking a sample process in the liquid vapor phase change. If we do it for liquid vapor phase change, we can also do it for the solid liquid and solid vapor also. So let us derive it for liquid vapor phase change here. So what I will do is I will take the concept of Gibbs function here. What Gibbs function tells is for a reversible process, Gibbs function is constant and it is not going to vary if the temperature and pressure are constant. At constant T and P, temperature and pressure, Gibbs function is going to be a constant value. So with this principle, we will try to derive the Clapeyron equation here. So for this process, we may say that the phase change at I, that is at T and P, will be Gi equal to Gf, Gibbs function initial equal to Gibbs function final. And for the phase change at T plus dt and P plus dP will give you Gi plus dgi equal to Gf plus dg at F. Okay, so this is what I have. Now let me call this expression as 1 and let me call this as expression 2, and I'll perform the subtraction between 2 and 1 here. I will take 2 minus 1. What it will give me is dgi is equal to dgf. So the change in g on the initial side is equal to the change of g in the final side as well. So if I have this here, g and f, we have seen in the previous class that dg is nothing but s into dt plus v into dp. Okay, so the derivation and all we have seen it in the previous class. I'm not repeating it here. Minus s dt plus vdp. Okay, so for m4, while doing the Maxwell relation 4, we have already seen how did we get this. So the same thing I am taking here. So since this is I side, I am putting I here, si and vi, and on my right hand side I will get s into dt plus v into dp. So s will be sf, v will be vf now. So from this I can get the expression for dp by dt, that is dp by dt, change in pressure with respect to change in temperature I am measuring. It's a kind of slope I am measuring on my PT diagram. Okay, this is my PT diagram. So dp by dt will be a slope here. So the dp by dt will now be equal to sf minus si by s, sorry, it's not s, it's v. Vf minus vi will get. Since your q is equal to tds based on your Clausius inequality, you can write that ds is equal to q by t, sorry, q by t. So here this ds is nothing but sf minus si in our case, and q is nothing but latent heat by the temperature. So in place of sf minus si, I can substitute this L by T here, so that my dp by dt will now become L by T into Vf minus Vi. So this particular expression dp by dt equal to L by T into Vf minus Vi is known as Clapeyron equation, or sometimes it is also called as Clausius-Clapeyron equation. Okay, so this is a general Clapeyron equation, and this Clapeyron equation must be written for various cases of your fusion. Clapeyron equation for fusion. The beginning we have seen that the fusion will happen between the liquid state and solid state. So here it's not working. Here in this expression we can see that now dP by dt in this case will be latent heat of fusion by the temperature into, in place of Vf I should write the liquid here, and in place of Vi I will have solid here, because I am now interested in the fusion. In fusion it will happen between liquid and solid, so that's why I have written it as liquid and solid here. Okay, now we can also write this expression for vaporization as well. For vaporization this expression will vary accordingly. Clapeyron equation for vaporization. This expression will now turn out to be dP by dt equal to, in place of L fusion you will have latent heat of vaporization by the temperature into the volume of vapor minus volume of liquid state. So that's the Clapeyron equation for your vaporization. Now we'll write the Clapeyron equation for sublimation. So if you write that here, dP by dt will be equal to latent heat of sublimation by the T into V of, that is a volume of vapor minus volume of solid. So these are the expressions for various cases. So the Clapeyron equation expressed in various forms. Okay, so that's all from your syllabus. So in your syllabus we have seen all the topics. So let us go to the top now. So now we have completed the thermodynamic relations completely, the Maxwell relations, the TDS equations, the Clapeyron equation, Joule-Thomson coefficient, all the topics are seen. Thank you.